Okay, so welcome to this morning's Zoom class on generative AI, literacy and application. You see the, oops, sorry. Okay, so you see this mind map in front of you? Okay. Now, over the past several weeks, I've been telling you that there are two key timelines with respect to the development of modern AI. There's one that I would call the language task, right? That's the one that starts with basically Alan Turing's imitation game, right? The idea that you've got an AI if you are able to fool a counterpart in a conversation that you are talking to a computer. Yeah, back then they didn't have a computer interface, so you couldn't fool anyone if you just had a computer, try to synthesize sound. So the way it was imagined was you write your sentence on a piece of paper, you send it under the door, and then you get a reply in the form of a written text or typed text coming back, right? Now, if it's written by a person, but the content would be generated from a computer. So the idea was basically that, number one, AI means artificial engine or artificial machine that imitates intelligence. And intelligence was restricted to the definition of human-like, okay? So it doesn't have to be intelligent conversation. It could be dumb conversation. But as long as it's human-like, and humans are considered the most intelligent animal on this planet, it's considered artificial intelligence, right? Now, the critical thing was that this essentially human, to convince that something is human, is to perform a language task. Right? It wasn't about, drawing or painting like a painter or, making a sculpture like an artist, but it's about carrying conversation. So this is the very first sort of like definitive way of demonstrating AI capability is that can AI perform language task? Okay. And in this case, it's not about voice synthesis, right? It's not about sounding realistic. It's about being able to respond, right, in a conversation. So that requires that it takes in whatever you say, right, process it, right, and then generate the response that is appropriate to the context. Okay, so you have to realize this. A conversation is only intelligent if it's in context. If I ask you, how are you this morning? And you give me a Shakespeare quote, okay? It could sound really intelligent on its own, but that would not be considered intelligent conversation because a Shakespearean quote or a explanation of quantum mechanics, that's not the proper response to how are you doing, right? So in fact, from artificial intelligence point of view, how are you doing? Fine, thank you, is a more intelligent or more appropriate response than quoting Shakespeare or explaining quantum computing, okay? Which you and I would agree is a lot more challenging otherwise. So that was the first thing. And we take this all the way up to today's natural language processing / large language model. So that's one timeline, right? The other timeline that I was telling you about is the vision task. Now that starts with our description of Hubel and Wiesel's cat experiment in late 1950s, early 1960s, right? And that basically culminates in my description on neocognitron and CNN, convolutional neural network, right? Again, neocognitron is a precursor to today's convolutional neural network. It does differ in that neocognitron is more like unsupervised learning, but convolutional neural network is based more on supervised learning. But the real crucial difference is that neocognitron was 1980s computer trying to run this program, whereas CNN, convolutional neural network, was run on GPU accelerated modern computer, right? That can do a lot of parallel matrix multiplication. Okay, so those were the two timelines that is crucial to understanding modern AI. Okay. Beginning with today, what I'm going to do is give you a beginning exposition on the other two timelines. Now, these two timelines are really, they're not independent. None of these are independent. I did tell you that the language task and the vision task technology crisscross, right? Crisscross back and forth between what's learned for vision task model becomes gets adapted to language task AI, and development on language task AI also benefit vision task AI. So they crisscross, they're not independent. Now, what I like to do is give you a heading description of the other two timelines. And if you understand these four developmental timelines, basically you understand how we got to today, okay? And these are basically the technology set, the sort of like state-of-the-art AI. Everything that you see in the news, advance in medical AI, robotics, in all kinds of stuff, to some extent, can be seen as an outgrowth or belonging to these timelines. Okay, not just one, but most of the time, quite a few. But there's like a developmental story. When I say development story, I mean one paper quoting another paper, referencing another paper, developing another paper. And as you know, tell you what. Now I understand that it's a little bit hard to view this whole screen, but it's easy for me, so I'm going to ask you to put up with me, okay? So things like, I'm going to go to the internet, and I say one of the reasons I say it's a continuous story is because you have something like this, okay? So let's say, right, so this is like an archive paper, right? So an archive paper, it's about, whatever, technology, some kind of technology. But what's important is that when you click on this paper, and by the way, this is what I would be expecting out of applied digital intelligence student to be comfortable working with, which is that pick up a technique from a paper, right? So let's do this, okay? So I just pick up some random paper. This one called Transformer Mechanism Mimic Frontal Parietal Gating Operation. Okay, well, this is kind of like sort of like, instead of AI being inspired by human brain, it's almost like now the AI model is inspiring what we understand about human neuroscience. So it's a very good paper. So let's say if I go to view PDF, one thing that you will notice, okay, let me make it big, okay. One thing that you will notice, let me minimize your space, okay. So the TA will, will check that you have the video and whatnot. But good. First of all, this PDF are very good. It's interactive. So when you read about this, you click and it goes immediately to the bibliography. Okay. But the thing that I want to mention, which this paper may or may not have. Okay, let me try. Let me find another paper. Sorry. Okay, let's something called diffusion model score base. Okay, Let's say that happened to be something that I want to look at. Manifold attracted. I happen to like this one. That's it. Okay, let's try this again. Okay, the paper comes up, and what you will notice is if I type in the word get, oh, I'm not having too much luck today. All right. Boom, 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 boom. Let's try this one. Okay, I'm not having too much luck. Tell you what, I'm going to go to my private patch. This is something that I downloaded a lot before earlier. So this is let's say AI or machine learning. So this is my folder on AI, and let's say I'm going to diffusion model. Let's say, and I click on this is a good one. Song and Herman. Okay. This should have it. There it is. Okay. So what happened is, this is a very typical way. Virtually all the modern AI research paper and technique progress in this way. So you have paper in front. Oops. Interesting. Okay, you have paper. And at some point, the author is going to say, okay, this is our methodology, blah, 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 blah. But if you want to, you can go to this side. Okay, it's a codes, and this is very important. Codes and checkpoints are available at GitHub. Okay, so what it means is that this paper was done using computer programs. Okay, that programs the AI algorithm, that their version, whatever it is. So this one is called something. This one is called what is it called? Generative modeling by estimating gradient of the data distribution. So this technique that they developed, not only did they describe it in terms of the methodology, like with mathematics, okay, this is how they describe their methodology mathematically, they actually share the code. So when you go here, you can literally go to their models, right? Well, you can actually check out the code, right? You can clone their site. So you actually have the algorithm they use to run. And this is very cool. To me, I mean, this is talk about scientific reproducibility. It's not just describing the methodology and the data that anybody can replicate and see if it really works, but then you have to write your own code. In this case, they give you the code. So all you have to do is just download this thing. Download this thing, download the data, download the code, run it, right? Now, that's not interesting to you if you think, well, all of this is just verifying that, the experimental result is correct. Okay, you're not trying to verify them, you believe them, so that's not of use. But what's of use is that now you can customize the algorithm to your need, right? So think of this as a function class. So all of a sudden, you have this technique. They say this technique is very good. And if you believe it's very good, not only can you verify that it is very good, you can actually use it on your own data. Okay, so that's how cool the world is. And that's in fact, it's something that you don't realize. That's what's driving this speed of innovation. It's not just GPU acceleration and investment by Google and all that stuff. It's this openness. Now, for final exam, maybe I should put in one bonus question. Why is it that OpenAI is an ironic name? That should be my bonus question for the final exam. Because OpenAI started out as as a sort of like a non-profit consortium for helping advance the development of AI, and they're very good. They're very smart. In fact, they authored the general GPT, ChatGPT, and whatnot. It's ironic because when they published GPT, they didn't share their codes, so they break with the tradition. They break with this wonderful tradition of sharing the code. It's only when other people start sharing transformer code that they kind of backtrack. I think that's the story. Okay. So anyway, that's kind of like a side story. Anyway, so let's get back to our story. Okay. Where are we? Okay. So all of this speed is happening, and this is like 1950s, right? But here, NLP, LLM, you would find when you search in this archive thing, thousands of paper, and they build on one another. They build on each other's code. Okay, they're not stealing. They actually say, we build this code based on somebody else's code. Okay? So everybody's sharing, everybody's acknowledging. Okay, so this tradition of computer scientists sharing their work, being open about it, open to scrutiny, open to criticism, and open to further development. Okay, so it's very good. Right. So again, same here. Hubbell Resource Cat experiment started in 1950s. And then you got this paper, Neocogniton, in 1980. But in 2010, there have been thousands of papers in Vision AI. Now, I have actually downloaded, let's say, just diffusion model. Let me see. There's only 64 papers. I haven't read them all. In fact, I haven't read most of them. A lot of time, I download them with the intention to read later. When it gets too much, I just download them with the intention of sharing them to students for projects and collaboration and whatnot. Okay, and this is a good one if you want to do project Vision Mamba. This is the nice one. Okay. Anyway, right. So let me close. Okay. So you understand how this works. All this, you will see that I have I write down the archive reference name. So literally, if you just take this, okay, and go to the internet, just go to the internet and you search archive, followed by these funny 10, 12 digits, you actually get to that paper. Deep unsupervised learning using non-equilibrium thermodynamics. Okay. So, deep unsupervised learning using non-equilibrium thermodynamics. I downloaded this earlier, but you don't have to rely on me. Okay. What I usually do for students interested in applied digital intelligence project is, instead of having them search all this paper, they can just come to my directory and look for things they're interested in. For example, if they want to work on convolutional neural network, I have a whole bunch of papers on convolutional neural network and techniques. Again, most of these, they're not just paper to read and be intelligent, but they actually give you links to their code, so you can actually use them. Okay, and that's that. The only downside is that you have to know a little bit of coding. Okay, but it's Python, so it's not that difficult. Okay. Now let's get back to this. Okay, so now what I want to do is give you two more developmental timeline, and for the next lecture or two, we will start having Pete Gongkan come in and start you on the workshop with the Diffie or Defy and the group project and the team project. And I will kind of switch in and out with how things work under the hood, how generative AI works. Okay, so, well, you can look at my hand. I don't know if I'm going to lose my hand. Okay, look at my hand. Remember that when we started, I think 2 weeks ago, I started to talk about how AI training, okay, I got to things like backpropagation. But even before that, I mentioned that AI, the way it's trained, it's not programmed as a finished product. It's programmed as an algorithm that learns to adapt its parameter based on data. So it's learning from data. It's learning from example. Therefore, we call that machine learning, right? We call that machine learning. And I briefly said, no, not briefly, I did go on and say that there are 3 machine learning paradigm, right? Okay, so I can write that. Maybe I should. Well, I'll just use Notepad to make it easier. Okay, easier. Okay, so you guys remember that 3 machine learning paradigm. Okay, okay, inspired by human child. Okay, okay, 1. Okay, so right, infant. What does that give us? Unsupervised. Well, it doesn't mean that you only do unsupervised learning only as an infant. I'm just saying it starts, okay? Unsupervised learning. Okay, 2. Okay, let's say toddler. Supervised learning. And 3, kindergarten. Okay, then you have reinforcement learning, right? Okay, now, so this is sort of like machine learning that was developed basically before my PhD, and for 10 or 20 years after my PhD, these were the active area. And then I did mention that there's a 4th machine learning paradigm that's kind of like incidental, or sort of like a part of AI algorithm that's not derived from human inspiration. And what do I say? What do I say that is? So 1, 2, 3, and 4. And what is that? That's called representation learning. So instead of being inspired in a way, it's sort of like developed from ANN, or artificial neural network, okay? Or deep learning, let's say deep learning era, okay? So, yeah, let's call it deep. Okay? Now, what does it mean? What it means is that instead of going from, so if you have something like supervised learning, okay, you're given a bunch of X, okay, and then you sort of like make cluster, maybe X here, this is kind of group X here, and another group X, okay, with a different tab or something, okay, so maybe this is 1, this is 2, this is N, K, okay, yeah, right? So in other words, you have a whole bunch of data and you start to basically form a cluster. So maybe something like that. That would be unsupervised learning. You're not told what to do. You're not told what to do, but you kind of like organize things around cluster. Now, supervised learning means that you have a whole bunch of X, Y pair, okay? And then you end up with neural network or machine learning, F, such that, okay, F of X is close to the real Y. Okay, so Y star. Okay, so that's what you want. Okay, so that's what you want. Okay, now this kindergarten, so this is environment reinforcement learning. You are given environment and some kind of like a reward, punish. Okay, and then you are given something like action is equal decision based on environment and state. Okay, right. So that's basically right. You work with data, you end up with a bunch of data. You work with data that comes in the form of input and output. So X will be input, Y will be output. And then you end up with approximation of a function. Okay. And recall that we talk about universal approximation theorem. Okay. Yeah. So you can always do this with arbitrary precision. So you're still working with, the raw form, the X, with the X. Now, likewise, as long as you can say environment in some kind of number, you still can work with environment, reward, punishment, and state. This is also a number. So for example, okay, environment is equal to kindergarten, state is equal to hungry, you're hungry, okay? And action, let's call it optimal action. Let's put a star on it. Action star is politely ask for food, or something like that, okay? Now, if your action is rudely steal somebody else's food, you'll be punished or something like that, okay? But anyway, so all this is still, working in the original space. So whatever the data comes in, you're kind of like working with that at the end, okay? Now, representation learning, the story goes a little bit like this, okay? Story goes a little bit like this. You have something that's kind of whatever, okay? I'm going to make it very generic, okay? So this X represents all of this. It could be a pair, it could be this, it could be anything, okay? Now, what happened is, okay? So what you want, okay, let's call this input, okay? And then some kind of artificial neural network that kind of like works on input and so forth, okay? So some kind of, so let's call it something like data and then AI task. Okay, let's put it this way, okay? That's what you want to do, data, AI task. Now, you still want to do this thing, okay? So data is in X, AI task is also in X, and on X, okay? That's still what you want to do. However, this is what representation learning does, okay? Representation learning is that you have something intermediate, something else, a new space, latent, I'm going to call it latent space, okay? And then AI tasks in latent space. And then you get back to AI tasks on X, okay? Original AI tasks, okay? So now, oops. Okay, can you see this? How do I hide this thing? Okay. Can you see this? Right? Say that again. The three machine learning paradigms that's inspired by human child, right? You have some kind of data or information, and then you want to end up with something that AI that perform AI tasks. Okay. Now, the AI task here is a clustering. AI task here is approximate input, output. The AI task here is to make the right decision about how to behave. Right? But essentially, you will notice that you still working, you end up working in the original representation, as it were. Okay. So if this were like population statistic, you end up with population statistics, right? If this were price of stock yesterday and today's price, well, you still end up with a function that predicts tomorrow's price from today's price. Okay? So that sort of thing. Okay? If this were about environment, how you should behave, this could be something like I'll give you another example just to make sure. Another example: environment is equal to street, and state is equal to left hand lane. Okay, so something like or maybe right most lane. Action is equal to keep constant speed. Okay, so this is why RL is very good for robotics and stuff like that. Okay. Okay. Now, so the key thing I want you to notice is that whatever the data it comes in, you're still working with that, right? But somehow, with this representation learning, in order to do this thing, it turns out that it's better or more effective if you transform X into some kind of latent space. And this is something like Z something. Okay? And you work with it, you play with it. Whatever you want to do, you want to do clustering, do it. You want to do a function approximation, do it, whatever. Okay, whatever you do it here. And then come back. Okay. Now, this thing here, this part, this chunk here is so good. Okay. It's so good. If you did it so well, you can do the following. Okay. You can do the following. You can actually do this once, and then you can do multiple tasks. So you can do multiple tasks, like task number 1. Okay. And then you can also do this, comma. Task number 2. Okay. So that's how cool this is. This is very powerful. Okay. So you can keep going, basically. Okay. Going. Okay. This part here is called representation learning. Okay. Now, why does it matter to us? Okay. Why it matters? 2 reasons. A, okay, by doing so AI tasks in latent space. Okay, latent means kind of hidden. Okay, does perform tasks really well in latent space. That's reason number one. Okay, reason number one. Reason number two. Okay, if you treat this as random possibility, you can generate. Okay, you can generate realistic, or you can generate realistic fake example. Okay, you can generate realistic sample from nothing. Okay, so right away, I don't know how keen or how bright you guys are, but you will see that this is the key to generative. Okay, so I'm gonna save this. Okay, this is called (3+1) machine learning paradigms. Okay, fourth one, critical, crucial for GAI. Okay, so I'm gonna save this and I'll give it to you. So before I forget. Okay, you should have that. Okay, so I share that. Okay. So the 3+1 is very critical. Okay, so back to our roadmap. So that is representation learning. Now, I'll come back. In fact, today it's about representation learning. So I'll come back to that. Finally, I have another timeline, developmental timeline called generative AI itself. Now, the reason I separate it here is because of this part. Okay. So I'm going to give you a short introduction to random generation. Okay. So today I'm going to give you a short, so I'm going to say new one, short intro to random generation. Random something generation. Okay. Okay, can you see that? So I'm going to do this using here. Okay. So first of all, I'm going to describe some distribution. Okay. My distribution 1 equal to normal distribution. I'm just going to call it my normal distribution. Okay. This is Mathematica. This is kind of easy. It's very easy. I'm just going to say my D1 normal distribution. I'm going to make another one, my distribution. You notice that anything that's black, it's kind of like a built-in function. So I'm going to say something like beta distribution. Okay, and hold on, let me check. Yeah, beta distribution, and then let's say something like 2 and 3. This is some parameter. Okay. what I'm going to do is plot my PDF of my distribution. So I do this first. So notice this is blue now. Shift enter, it becomes black. So now it's understood. So now I can use it. My distribution X, okay, from X from -3 to 3. Okay, there. Oops. Distribution X. Okay, there it is. Can you see that? Okay. Let me be a little bit fancy and say filling to axis. Okay, so can you see that? Okay, so that's my distribution. What it means is that my data is randomly generated, my data, okay? You find most of my data between 0 and 1, sometime a little bit up here, okay? So let me try this with my distribution 2. Now my distribution 2 is going to be a little bit limited. It's actually like this, okay? So let's see, I can make something more interesting. Oops, sorry. That's not good. Too fancy. Yeah. Okay, so notice I have two different distribution. Okay, I have two different distribution. Now, normally the way statistician work is that they get real data. Okay, so how statistician work? Okay, number one, get data. 2, get maybe plot histogram if you can. 3, hypothesize distribution, e.g. normal distribution mu sigma. Okay, and number 4, okay, fit distribution by tuning parameter, i.e. mu and sigma. Okay, that's how statistician work. Okay, so right, so this would be something like now. Okay, you get the data from real world. Okay, okay, this is how statistician work. Okay, this is how simulation or simulator work. Okay, simulator. Okay, let's not make person. Let's make how statistics work and how simulation work. Okay, 1, you assume distribution with specific parameter, i.e. normal distribution, what is it? Like 0 and 1. Okay, this is literally what I did. Okay, 2, okay, generate, okay, let's say n equal to say 1000 number with probability given by above. Okay, by assume parameterized distribution. Okay, that's it. Okay, and now you have n equal to simulated or fake or augmented or data from computer. So it's not from the real world, right? So you used to have real data. So now you have get actual real historical whatever. Okay, does that make sense? And now number 4, you can plot histogram if you like. So that's it. Okay. Okay. So for example, let's see what happened. So now I have this. So let's say I have this. So what I'm going to do is my generated data 1 is equal to random variate. Okay, random variate, and I just put in my distribution. Okay, and how many do I want? Let's make it 1,000. Okay, there it is. Okay, I can make it 10,000. Okay, I can also do this with the second one. Okay, 10,000. It's 5,000. Okay, this semicolon just say, don't show the result. And now what I'm going to do is I'm going to plot histogram of my generated data. See? It has that nice shape. It looks just like this. So in a way, this is the opposite of statistician. Statistician have real number, see that it's got this shape. So I say, well, let's call it normal distribution and then fit the parameter. So let's try to do the same thing. So let's see what happened when I have this. Number 2. See, it's got that between 0 and 1. 0 and 1. Right? So this is the reverse. Now, what's crucial? What's crucial is this. Key point. The simulated or generated, I'm going to use the word generate, data looks real. Okay? And in fact, you can use it and can be used just like real. Okay? Can be treated as if it were, these were, data is plural, right? Singular, plural. Okay? So take this as okay. Give it to you. Now, so what's cool about this? So A B, this is the same kind of thing we want from generative AI, right? Same kind of goal we want to from generative AI, right? So, in other words, something not real, something created, but convincing as if the real thing. Okay, now you can nod your head. I'm not going to shake your head, but your TA can see you nod your head. So that's the key thing. That's the key thing. And that gets back to this timeline. Okay. Now this thing I call PRNG. Okay, I'll make a quick note. Note. PRNG is equal to pseudo random number generation. Okay. Yeah, pseudo number. So what it does is exactly what we just did here. Okay. Now, let me show you what I mean by pseudo random. Okay. Pseudo random. So let's say I'm gonna say let's generate 5. Okay. So notice it's a random number between 0 and 1 because this is from this distribution. Okay, 0.6, 0.4, 0.4, 0.6. So let's generate it again. I'm getting a new number. Okay, so it's random. It really is random to your eyes. Okay, you can't. Can you predict what the next 5 number is going to be? What the next 10 number is going to be? There's no way. There's no way. Okay, but here's a big but. It's not really random. The computer has a deterministic way of generating. So how can you know this? How am I going to tell this? This is what I do. Okay. So if I do this, it's going to keep generating new numbers. It's going to look random to you. But watch this. What if I want to seed random? This is kind of like a starting seed. Put in some number. Okay, doesn't matter. Now, this is sort of like to set the beginning. This is kind of like my beginning sequence or something, whatever. Okay. If I set this seed, this random number is going to be this. Doesn't matter how many times I regenerate, I'm going to get the exact sequence. So it's not really random. Okay. I.e. pseudo means looks random, but really deterministic, generated with an algorithm. Okay? Okay, so that's done. Okay, so let me add this to you guys. Okay, you should have this now. Your line in your line. Okay, so back to here. Okay, back to here. Right. So what's going to happen is, what's going to happen is, oops. Okay, let me Let me look at your face, see if you're still with me and you're still okay. Okay, how many of you are totally lost? I can't see your face. You have to lower your cameras. Okay, whatever. Cleo, Artist, Nat, all these people, lower your face or lower your camera. Nene, Ford, Prem, Ploy, Un, Rung, Tom, Un. Are you still here or you just took off? Okay, so TA, if you can't see anyone's face, you can mark that person as absent. For example, I think okay, a lot of these are absent. Okay, TA, are you still with me? TA ครับ
Yes,
Okay.
Ajahn. But I have a problem with your gut. I cannot find your ID in my student list. So please check your ID, please. Your ID number in the screen is 7580888056, but I cannot find in my student list. I just message you in the chatting in Zoom. Please check your ID, your gut. Your gut is, I think, your nickname.
Okay, good. Okay, so make another round of attendance. If you can't see the face, then you can just mark it off. Okay.
Yes.
We actually thinking about developing this kind of add-in to Zoom so we can do online. This was something that was critical when we had this COVID, but the idea it's not necessary anymore because most of the time we meet in person. Okay. But anyway, so for example, I think this 16758 31256 is no longer here. There's a lot of people who are no longer here. Okay. Show me your face, guys. I don't know why you're hiding. I know you haven't put on makeup or anything, but there's a lot of you who are boys. I don't think you need to put on makeup. Okay, so don't be shy. I don't really want to look at your face as much as I want to see that you understand. So far, do you understand what's going on? Hello? Never mind. I'll just keep going. Okay. Okay, so now. Okay. So back to our slides. Okay, back to our here. So what happened here is before you get to here, right? So you can say something like you have to get to something like multi-layer perceptron MLP and okay, and so on. Okay, so let's do that. Now, what happened here? What happened here is, okay, take a deep breath. So this class is going to be divided into 3 shots. Okay, so let me stop. Let me stop recording.